Hello and welcome to this Shapes of Molecules Chemistry Olympiad question walkthrough. It's from an older paper. It's the second paper that was ever taken. The Chemistry Olympiad in the UK started in the year 2000, but it's an interesting one because it's got three quite straightforward examples and two quite hard examples, so it kind of draws you in with easy ones from your recall and your flashcards and then really makes you think, just like many Chemistry Olympiad questions do. So it asks you to draw the three-dimensional shapes of 5 molecules and mark any non-bonding lone pairs and bond angles. So normally what we do with shapes of molecules is we look at the central atom and see how many lone pairs and how many bond pairs it has, and we can work out or remember rather, the appropriate bond angle and shape that goes with that. So if we start with a straightforward one from many A-level chemistry textbooks, you draw the dot cross diagram. That's a good starting point. The central atom is obviously nitrogen, and you can see 3 bond pairs and 1 lone pair. Therefore that would be pyramidal 107 degrees. So this is the three-dimensional drawing. Has a wedge and a dotted line. The dotted line signifies the NH bond going into the screen. The wedge signifies it coming out of the screen, and the solid line from N to H on the right hand side is basically in the same plane as the screen. So just to recap on that, this one is going into the screen, this is coming out of the screen, and this is in the same plane as the screen. So each of these bonds here is one of these bond pairs obviously, and this lone pair here gets put on top of the nitrogen as 2 dots. So doing the same thing for water, you end up with something like this. Now because water is non-linear and there's only 3 atoms in it, it doesn't have a three-dimensional aspect in the same way that NH3 does. So you can just draw it without any wedges or dotted lines. With BF3, this one is rather interesting because the boron has 1, 2, 3, 4, 5, 6 electrons in its outer shell, which is a little unusual. But that's not the remit of the question. They're literally asking you to deal with what we have in front of us. So boron has 3 electrons in its outer shell because it's in group 3. It'll form 3 covalent bonds, leaving no lone pairs. So it'll form a flat, or what we call in chemistry, a planar structure. So this would be trigonal planar, is the name for the shape, and it's 120 degrees bond angle. 120 degrees being the angle that allows maximum repulsion or maximum space between the atoms. So the electron pairs get as far apart as possible. So those are the 3 that are quite straightforward. The next one is a little bit tricky. So we'll put the structure for BF3 elsewhere on the screen, just move it up a little bit. And let's look at NO2. So NO2 is a common enough molecule. It's called nitrogen dioxide. It's actually a pollutant in air. Many urban areas around the world suffer from elevated levels of NO2 from engines, diesel engines in particular. And it's a cause of asthma, lung disease, and some people think it's actually potentially related to lung cancer as well. But we're not 100% sure about that, but it is quite a well-known pollutant. It's also a very powerful greenhouse gas. So to start off, when you're drawing a shape of something you haven't come across before, try to draw the dot cross diagram. So the way to do it is to obviously put the overlaps between the shells like that, and then you can put in the number of electrons that each individual atom comes with already. So oxygen's in group 6, so it has 6 electrons per atom of its own. Nitrogen is in group 5, so it's got 5 electrons of its own. So a little bit of playing around will quickly reveal that you can't have 8 electrons in every atom's outer shell. So this is where this is a bit challenging. So what happens if you're in that situation? Well, you consider the electronegativity of the atoms concerned. So oxygen is more electronegative than nitrogen. So anything that will enable oxygen to have 8 outer shells is 8 outer electrons rather, is preferable rather than nitrogen having 8 outer electrons. So it's commonly drawn with a data covalent bond between the nitrogen and an oxygen, and a double bond between the nitrogen and the other oxygen, and then the remaining nitrogen electron gets put at the top there. So it's just here as an unpaired single electron. So that means nitrogen has an incomplete outer shell. You can see if you count it up, it's got 7 electrons in its outer shell. So if you're able to live with that, we can then construct the rest of the molecule by putting in the electron pairs in the outer shell of the oxygen. So remember, oxygen is more electronegative than nitrogen, so the oxygen will take priority in getting full outer shells over nitrogen. So how do you draw this? Well, it's a little bit like a linear molecule, except there's a little bit of repulsion, so it's a bit less than 180. Not massively less, but a reasonable guess might take you somewhere like 130 to 150 degrees. Now ClO2 minus, you've got to be a little bit careful when you're looking at oxyanions like this, because they put the minus sign to the right of it, but that doesn't necessarily mean the minus charge is on the oxygen. The extra electron that's responsible for that minus charge could actually be anywhere in the molecule, or in the oxyanion I should say. Okay, so let's start off again. If we look at the chlorine, it's got 7 electrons in its outer shell to start with. Oxygen has 6 electrons in its outer shell. So what will happen is that chlorine takes the extra electron. So again, it's got a lone pair on one side, it's got a data covalent bond on the other. It's similar to the NO2. This is deliberate in the question because they've already made you think a little bit about NO2. And with that kind of structure, with a data covalent bond on one side and a double bond on the other, you could actually apply it across to this as well. Not forgetting, of course, that you now have 2 lone pairs on the chlorine. So this now follows a similar model to water, doesn't it? So it's 2 bonding regions and 2 lone pairs. Now in shape theory, you can actually say that a double bond could be considered a lone pair, a bonding pair. But in actual fact, there are 2 pairs of electrons there clearly. So that's why sometimes we call it a bonding region rather than a bonding pair. So I'm going to talk about a bonding region as either a single or a double bond. So 2 bonding regions, 2 lone pairs, and I'm going to put in my extra electron here so you can see clearly where it's gone. Okay, so hopefully this has been a useful look, not just as shapes of molecules, but some more complicated examples and some other considerations that go towards deciding what those shapes are going to be in those cases. As always, thanks for listening. Until next time, see you soon.